Okay, let's start. Today we are happy to have Hiraku Nakajima from IPMU. He'll be giving a lecture series consisting of 3 talks on geometric Satake correspondence for affine Lie groups.
Okay, thank you very much. I'd like to thank organizers for invitation to giving the opportunity to talk here. So I will give 3 lectures on geometric Satake for affine Katsumudi groups. And today I will review the definition, mathematical definition of Coulomb branches, and also I explain several examples. And I put the Dropbox share link to the chat box. So if you click this page, then you can see the update note of my presentation. Okay, so I will basically follow the notation in Glimmer's lectures, maybe slight changes. But there's one important difference. So I do not assume good or ugly conditions, which Glimmer assumed always. And also, if you hear Hanani's lectures, he also assumed good or ugly conditions. But for geometric application to geometric Satake, it is crucial to don't assume these conditions. So let us start. So G is a complex reductive group, and GC is a maximal compact subgroup. And I take N, a representation of G, complex representation of G, finite dimensional one, and I denote row homomorphism from G to GLN. And then I consider representation M, which is a direct sum of N and its dual. This is symplectic representation of G. So I'm considering the symplectic representation, which we call of cotangent type. So this is not arbitrary symplectic representation, but we are only concerned with this type of symplectic representation. Then you can assign 3D n equal for supersymmetric gauge theory to that. Okay, I continue several notation. So G tilde is some larger subgroup which contains G as a normal subgroup. So this is normal. And G tilde still acts on N. And GF, the quotient group, is called the flavor symmetry group. And quite often I consider its maximal torus. So I denote by this TF. And what people call mass parameter. So this is element M in the Lie algebra of TF. Okay, and sometimes we also consider M. I use the same letter form of C star of TF. So for more precisely, so if I consider the derivative of M, then I get the element in the Lie algebra, but I use the same notation for this. So this is a mass parameter. And I define TC. So this is a Pontryagin dual. To pi 1 of the group G, gauge group. G is called gauge group. Pi of G. So this is homomorphism group, space of group homomorphism from pi 1 of G to C star. So in our example, which I explain later, so pi 1 of G is always cyclic group of finite rank. And if G is a semi-simple group, as usual, then pi 1 of G is a finite group. But those examples which we will not discuss in these lectures. We usually consider the case when G is the product of general linear groups. Then fundamental group is a cyclic, infinite cyclic group. Then Fy parameter, which I denote by zeta, is an element of the real algebra of TC. Or as above, maybe form of C star to TC. So these are another set of data. Okay, then I first explain the Higgs branch, which is easier to define. So Higgs branch is a symplectic reduction of simplex vector space M by G. So I use this triple slash notation for symplectic reduction. Or it is the same as if I put the cotonic inner product on M, this is nothing but the hyperkähler quotient. So I will use a algebra geometric technique later. So I prefer the symplectic reduction rather than the hyperkähler quotient. Okay, and then this Weber symmetry group, GF, acts on the Higgs branch because you have the larger group G tilde acting on N and also on M, which is in the cotangent bundle of N. And GF or GF is a quotient group, and we are taking the quotient by G, so this quotient group acts on the quotient space MH. So this is clear. So in this context, so mass parameter, so which is the element of the real algebra of TF, is considered as an equivalent variable. So we equivalent. Oops. Let's see. Somehow. My software. Okay, maybe, let's see. For some reason, my software stopped working, but it's okay. So I'll try again. Okay, I just introduced equivalent variable. So in tomorrow, I will consider the equivalent cohomology of the space Higgs branch MH. Then M element in the real algebra appears as equivalent variable. Okay, and Fy parameter. So data in the torus TC. Or maybe here it is better to consider as form of C star to TC. So since this is TC is defined as a Pontryagin dual of the fundamental group, so this is isomorphic to pi 1 of G2, and also I replace C star as pi 1. Of. So C star is a Pontryagin integral of Z, and this is Z is a fundamental group of C star. And this is, you can check that this is isomorphic to the group of homomorphism from G to C star. And this isomorphism is just given by taking pi 1. Okay, then, so if you consider the real algebra element is D of TC is considered as homomorphism, space of homomorphism from the algebra homomorphism of gate C. So then one can deform the momentum application. So moment map is a map from M to the real algebra, dual of the real algebra, which is central in this, I mean, that's contained in this space. Then the symplectic reduction was defined mu inverse 0 divided by G in the sense of geometric invariant theory. But so instead of this, you can consider mu inverse of zeta divided by G. So this I denote by MH of zeta. Or in this point of view, so this one can consider GIT quotient. So mu inverse 0 divided by G, but in the sense of geometric invariant. Or if you are not familiar with these kind of things, then you can also consider this as a hyperkähler quotient. And you can regard zeta as a imaginary quaternion value, imaginary quaternion tensor with the center of the real algebra, and you can part out the hyperkähler. So in this sense, those Fi parameters, zeta is a deformation or a Kähler parameter. So it is a deformation parameter if I part out the momentum application, complex momentum application, and it is Kähler parameter if I change the stability condition. So any question? Okay, then I go to the Coulomb branch. So I use the definition, mathematical definition, given by Weber and Finkelberg in my joint work with Weber and Finkelberg. So I first consider this affine Grassmannian. Associated with G. So this is the modular space of pairs. So first one is P. So this is principal bundle, principal G bundle. over the formal disk. So this is spectrum of formal power series. So if you're not familiar with this, then you just consider this is a very small disk in complex line. And the second ingredient is phi. So this is a framing, which is trivialization of this bundle P. But not on the whole B. So this D times is punctured, formal punctured. So this is spec of C of formal Roland power series. Okay, so let me explain it again. So affine Grassmannian is a modular space of pairs. One is principal G bundle over the formal disk, and the other is its trivialization on the puncture disk. So people draw this picture. So you have two disks, two disks, very small disks, glued along. The puncture disk, and you have principal bundle over the upper disk P, and you have trivial G bundle over the lower disk, and they are glued along D times. Okay, so affine Grassmannian is this kind of object. Then I consider larger space. This is modular space of triples. So P and phi are same as before. But new ingredient is S. So this is a section, holomorphic section of the associated bundle, P cross G to the N. So recall, N is a representation of G. And if you have a G bundle P, then you can consider the associated bundle, and you can consider this section. So then you impose the following condition. So by this framing, you can send the section by this phi. So then this is a priori, this is element in the formal n-valued formal power series, but I impose the condition that this extends across 0. So it means that, so S is a section of this bundle over this T. So this object is often called raviolo. So this is something you can find in Italian pasta. So this looks like a little bit about raviolo. So we call it raviolo. Okay. So then we have an action of G of O. So this is gauge transformation. For trivial bundle. So it acts on this space R. Okay. Then we consider the so-called equivalent Borel-Moore homology of the space R. So R is an infinite dimensional space and GO is an infinite dimensional group. So you must be a little careful how they are defined, but you can approximate those varieties and groups by finite dimensional objects. And so you can approximate this equivalent homology group by equivalent homology group of finite dimensional object, which is well defined. And you can just check the limit is also well defined. So we define in that way. And then this space is a mathematical justification of what physicists consider the ring of monopole operators. So this is. So in particular, this has the structure of algebra. And this is not very natural. One can define associative product on this equivalent polynomial homology by the convolution. So the idea is the very well known one. So I consider triple disks glued along the formal disk, punctual disk. Then you consider the modular space on bundles on this one as above. Modular space paired modular space bundles and sections. And then you have 3 projections to this. You just forget one of the disks from among 3. So you get 3 ways of project. So I did P1, 2 for when I pick up the 2 first disk and the second disk. Then you can pull back the homology class here by P1, 2 and P2, 3 and take the intersection pairing on here and then push forward. So this is a very rough idea. And you can justify this. You can rigorously define this protocol. Okay. Do you have any question or comment? Okay. So as I said, this is the ring of monopole, what physicists call ring of monopole operators. So let me take a few minutes. Why this is so? So I recall Jacques at this lecture. So his first lecture. So he explained the magnetic monopole and a relation between magnetic monopole and bundles on Riemann surface. But in our case, the Riemann surface is something very simple. So we just consider monopoles on R3. So I decompose it into R2 cross R, and I identify R2 with complex numbers, and so I denote the coordinate called C by Z and R by T, so T is the time coordinate, and I denote this kind of figure. So this is C and this is the T. Then the monopole equation F with star is d phi, dA phi. So this is our monopole equation. So then there are several components, but one of the components is number of t plus I. So I number of t plus a connection. So 0, 1 part of nabla on this complex line is parallel with respect to the connection in this time direction. So this is one of the consequence of multiple equation. So it means that the holomorphic structure on the slice, time slice, is constant along time direction. Then we allow singularity at the origin. So this monopole with singularity was studied by Coulomb a long time ago. Well, maybe not so long time, so it's 1985. So this can be understood as S1 equivalent instanton, so which is 4-dimensional object. So you have S1 action here, so which is preserved. I mean, R4 is a quaternion, 1-dimensional quaternion vector space, and S1 is preserving this quaternion. So you have you can consider this as a hyperkähler manifold, and S1 is action preserving the hyperkähler structure. So then you consider the hyperkähler momentum. So well, more concretely, this is some very explicit quadratic map. And if you take two spheres around the origin, then this is, if you restrict to the two spheres in R3, then this realize the Hopf relation. So then if you have instantons on R4, which is equivalent under S1 action, then it descends to a connection on R3, except the origin. So because origin is a fixed point of this S1 action. So as a monopole on R3, so you will see the singularity. But anyway, so from this description, so you can understand the type of singularity. So this is described by the fiber, the action, S1 action on the fiber at 0 on R4, up to conjugacy, up to gauge. And this is nothing but homomorphism. So S1 to G, or maybe S1 to DC, up to conjugate. Right, so this is a co-character. And this appears in for example, in the definition of in the Hecke correspondence in geometric Satake and geometric Langlands. So if you have a singularity at here, and you consider again the slice for each time, and if time is negative, and if you don't across this origin, then by the same reasoning as above, the holomorphic structure remains constant. And if you consider only positive time, then the holomorphic structure is the same, but the holomorphic structure changes. So by this, and if you just to consider I mean, this is, you don't need the global analysis. So this is some story about the small neighborhood around the C of Z. And the time is, you don't need to all the time. So time is could be just a small number around 0. Then it looks like this picture, right? So D is so this here, in this analogy. So this D corresponds to T positive, and this lower TD corresponds to T negative. And as I said, so it's, if you don't cross 0, then the homological structure is the same. So you can regard this as a single disk and 2 disks for positive and negative. And if you consider a point far away from the origin, then this singularity doesn't cause any trouble. You can still have the identification of homological structures. That means that you can identify this homological structure for T positive and T negative outside the origin. So in this way, you can just recover the definition of Langlands. Sorry. So since my program just collapsed once, so you cannot see the. Well, I mean, of course, I can. If I can take some time, I can construct a link again. But should I do right now? I mean, it takes some time.
Not sure. Maybe not worth it.
Is it okay?
Yeah, it's okay. I just wanted to let you know in case.
Yeah, I know the problem. I mean, it doesn't happen often. I mean, usually don't problem. It doesn't cause any problem. But this time the program crashed, so I cannot use the same shell.
It's fine as it is. I just wanted to let you
know. Okay. Any question for? So I hope this clearly explain. And this is, maybe I also mentioned this is a correspondence. Well, I mean, for today, G is arbitrary, in fact. So I will explain the example, but so far the construction is arbitrary. You don't need to assume G to be product of unitary group. Okay. So this equivalent, I hope now you understand this. R is a ring of monopole operators. Yes, and also I think somebody asked when during the witness lecture, somebody asked how the adjoint, how Higgs fields are regarded on the Higgs band. Higgs fields should be treated on the Hecke correspondence, and this is my answer. So the section is, you should not consider section as a section of either bundle, but S is a common section of 2 bundles, which you modify. So you have 2 bundles, which another is obtained by modification, and S is a common section of bundles and modified bundles. Okay. And then the theorem, this product. So this is, I mean, there's some general machinery of the general theory of the convolution product, and this is associative. That is not surprising at all. But the surprising fact here is that the product is commutative. So if you consider this kind of product, convolution product in different setting, it's usually not commutative. And also if you consider the so-called quantization of the Coulomb, it's not commutative. But in this particular case, without a quantization, this is a commutative. And there's some simple reason if you believe that this is the ring of monopole operators. So we have Z plane, and we have time direction. And make a modification at t equals 0. And when I consider the product of two operators, somehow, how to say, the actual point is that somehow you can. So if I just consider this, the origin is a origin of the formal disk, then you cannot move. But in fact, as I explained in this picture, this D is in fact a positive radius. And I mean, the point is somehow how to say, so in this description, so you don't need to assume disk to be of radius 0. And you can also argue this actual disk or even actual complex line. And then one can move origin freely. So there's no ordering on this ordering. So that is the reason why you get a commutative product. So if when you consider the quantization, then you also consider the rotational symmetry in this along this axis, or maybe the rotational symmetry on the complex line. Then your singularity is only allowed to on this time axis. So you cannot change the ordering. So that is the reason why the quantization is non-commutative. So anyway, this is commutative. So you get commutative ring in this way. So once you have commutative ring, you can define the Coulomb branch as a spectrum of this commutative ring. So this is an abstract definition, but once you have the commutative ring, the algebraic geometry tells us you can recover the space. So that you can consider that this original ring is the GO, is a ring of functions, or maybe polynomial functions. So this is what the scheme theory tells us. And strictly speaking, unless you assume several properties on this commutative ring, MC is just a affine scheme, and it is maybe far away from the usual varieties. But in this particular case, you can also show that this commutative ring have nice properties such as finite generations and irreducibilities and so on. And finally, so this MC is the usual algebraic irreducible algebraic variety. Okay. So any question? Okay, then I want to explain the FI parameters and mass parameter in this. In this definition. So R, so you consider the connected component of the space R. So this is isomorphic to connected component of the affine Grassmannian. Because you just add the section, the section forms a space, vector space. So for the connected component that plays no role. So this connected component is the same as affine connected component of the affine Grassmannian. But so this is a so in topology, this is same as the space of based roots to GC. So this is the same as fundamental group of C. So this is the reason why we define the TC flavor symmetry for the Coulomb branch symmetry as a Pontryagin dual of pi. Yeah, a little bit more precisely. So H star of G of O over R. So R is some space. So it the homology group of space decompose according to connected component. So connected component is right. So it means that this commutative ring is graded by fundamental group of G. So it means it's Pontryagin dual. Acts on MC, right? So you consider the space of functions, and so you can consider this decomposition as a weight space decomposition with respect to this action T, and it is parameterized by Pontryagin. Okay. So contrary to Higgs branch, so FI parameter in the Higgs branch was deformation and the Kähler parameters. But here FI parameter plays a role of the equivalent barrier acting on MC. On the other hand, I consider mass parameter. So as I said, I consider G tilde, which is larger than G, and maybe I just consider the case this quotient. I denote this quotient by G of F, but I assume this is exactly equal to here. Then we replace G by G tilde in the above construction. So the variety R is defined by considering G modular space of G bundles together with sections. So, but here I consider the G tilde bundles, and N is still representation of G tilde. So all the construction doesn't make sense in larger group G tilde. So then you can have M of G tilde and Coulomb branch of G. By applying this construction. Then, so this is, so you have the action of pi 1 of G tilde Pontryagin dual of this acts on this. but you have the quotient, this pi 1 of T of pi 1 of TF is a you have the homomorphism from pi 1 G tilde to pi 1 of TF, but we are taking the Pontellier linear, so you have the group homomorphism in the opposite direction. So you have the action of this group on this Coulomb branch, and this is nothing but the dual torus. So you have a torus, and you consider the fundamental group and take the Pontellier linear. This is nothing but the dual torus. So dual torus is acting on this Coulomb branch, and you can show that the original Coulomb branch, MC of G of n, is a symplectic reduction of this larger Coulomb branch with respect to this torus action. So this is not, I mean, if you just go through the definition, our definition of Coulomb branch as a spectrum of this convolution algebra, you can show this lemma. So in particular, if you have dual element of the dual torus, which is nothing but the algebra of TF, and the mass parameter is as explained in the beginning, is an element in here. If you have an element here, then you can consider the deformation. And if you consider the group element in the group of homology, you can also consider the GIT quotient. So you can consider deformation of Kähler parameter. OMG. So again, the role of the mass parameter is opposite, is exchanged for Higgs and Coulomb branches. So Fy parameter was equivalent to variable in the Coulomb branch, and this was Fy parameter was deformation on the Kähler parameter in the Higgs branch. And the mass parameter, it was equivalent variable for the Higgs branch, and it is deformation Kähler parameter for the Coulomb. So this is the end of my explanation about Higgs and Coulomb branch. Any question or comment? Okay. So so far, this is very general construction. It works for arbitrary. Maybe I should also mention that. Let me see. Where it is. Yeah, this definition. So this definition was motivated by Hanani's and his collaborators' monopole formula, and in particular, so this. So if you compute the Poincare polynomial, so this is a graded ring, so graded by homological degree. And this homological degree plays a role of extra cyst action, which I don't talk about today. But anyway, so if you consider the monopole formula is a Hilbert series for this cyst action. And this cyst action corresponds to homological degree. And monopole formula is related to Poincare polynomial of this. But as I explained, so this monopole formula is well defined only for good or ugly theory. But it is simply because in our definition is more general, and this it's not well defined because if you pick up particular degree, this homology could be infinite dimensional. So that's the reason why the monopole formula in general doesn't make sense. But still, our definition is, is perfectly fine. Even this is infinite dimensional space. R and GO is infinite dimensional manifold and infinite dimensional group, and homology group is infinite dimensional space. But as I said, we approximate the space by finite dimensional ones, and if we don't take the limit, this is well defined. The actual object which you are working on is a finite dimensional. So this is always well defined. So infinite dimensionality only appears when we take the limit. Okay, any question?
There is a question, but I think maybe you can just talk about examples and then discuss this question after the talk.
Okay, let me see. Okay, examples. So this is secretly the quiver gauge theory of type A1. So I will introduce quiver gauge theory tomorrow on Wednesday. So you usually denote circles and cross, E and W. So G is GLV, and N is form of CW to CP. And I use the following notation. Lambda is W, and mu is W minus 2V. So this I consider as weights of SL2. So this is the real algebra associated with A1 quiver. So if you forget this framing nodes, then you get type A1 thinking dagger. Okay, then I first start with sixth branch. So MH of lambda mu. So this is, if I don't put Fy parameter here, then I just consider the non-perturbed one. Or maybe Fy parameter, I just take 0. So this is X and the monotheism matrix of size W times W square matrix, and X square is equal to 0, and the rank of X is smaller or greater, smaller or equal to B. And this is the cotangent boundary to Grassmannian of VW. So Grassmannian. Three planes in CW. So this is very easy to show, and I proved it a long time ago. So we have map like this because I was taking cotangent, and also X is B times A, and in this case B. So this is the first case, and so if we put zeta, then B is injective. So this image of B is subspace in CW. So this is roughly the correspondence. And you also have the map I only, maybe I should also say that this is, I only consider the complex part is equal 0. So I only change the GIT stability part and the complex. I put the deformation parameter to be 0, but I only change the scalar parameter. So in that case, I have a homology. Morphism, projective morphism. So you can consider potential boundary to the pair of this subspace and also this X, and you just remember this X. And the fiber is basically the Grassmannian. So this is the project morphism. And you can also check this. This is surjective. If and only if 2D is less than or equal to W. So this is a good or ugly condition. And in terms of those weights, this is non-negative mu. And also maybe I should, before this, I should also say that this MH zeta is non-empty if and only is smaller than or equal to W. So I consider Grassmannian V planes in CW. So V cannot be larger than that. So can I take a few more minutes to explain the Coulomb branch?
Yeah, I think you can take like, say 5 more minutes.
Okay, thank you. So I can deform by mass parameter. And contrary to the previous case, this is always birational. For arbitrary lambda mu. And so I'm usually interested in this one, which is I set the mass parameter to be 0. So interested in this. In tomorrow's lecture. So I will describe this MC of lambda because of this reason. And one easy way to understand MC lambda mu is you use Bow variety. So which I will explain tomorrow more in detail. So this is my work with Takayama. And then you use the so-called Hanani-Witten transition. So if you're a physicist, maybe you know how to understand the Coulomb branch of this case by using deep brains and NS brains. And you don't analyze Coulomb branch, and you use Hanani-Witten transition. And so these Bow varieties and my paper with Takayama just create Hanani-Witten transition in mathematical rigorous way. So anyway, MC lambda mu. So at least if V is strictly smaller than W, so then you can describe. I mean, this condition is somehow related to this non-emptiness in the Higgs branch. So this is described as the space of matrix like this. So we have two block nilpotent matrix V of W. So this is the starting point, and you perturb this matrix slightly. So this is related to the concept of slice. So this red entry is its arbitrary numbers. So if you don't put any further condition, then this is just a vector space because those red entries are arbitrary complex numbers. Other entries are there. You impose the condition x is nilpotent. So if you impose a good or ugly condition, then you can show that this above is isomorphic to intersection of so-called Slode-Wills Slode-Wills to the nilpotent orbit, which is given by all red entries with 0 and nilpotent con. A kind of variety which appears in geometric representations very quite often. But in general, so you can have some entry between W divided by 2 and W. So if V is in this range, then the above space is larger than Slode-Wills. So this sign, this is W minus T. So I compare the size of the matrix, nilpotent, size of two nilpotent matrices. And if V is, so this condition means this is smaller. But somehow, if you look at it carefully, the number of red entries is somehow different if you swap V and W minus V. So because of this reason, so the Slode-Wills, even if you exchange V and W minus V, nilpotent matrix doesn't change, but those space which is given by red entries are different, and this is larger. So because of this reason, the variety is different. But anyway, so you have this kind of description. And you can also, in this example, maybe this is exercise, one can study stratification or symplectic leaves of MH and MC. So maybe MH is easier. So MH is so you have so this is a square zero matrix with this rank condition, and the smallest one is corresponding to lambda equal mu is equal to lambda, which means V is equal to 0. And the next one is MH of regular of lambda and lambda minus 2. So this means X rank 0, X rank 1, and so on. So MC is a little bit more complicated, but somehow the end result is like this. So you have not MC. MC of lambda mu. So this is regular locus, open subset. And the next one is naturally isomorphic to you replace lambda by lambda minus, and so on. So in the Higgs branch, you change the second entry, lambda minus 2 and so on. But in the Coulomb branch, you change the first entry from lambda to lambda minus 2 and so on. So you have the reverse, so reverse, order reversing projection between strata. And if you look at more carefully, then this Coulomb branch, it corresponds to this is a Coulomb branch of some gauge theory. And this gauge theory it appears if you consider the transversal slice to the corresponding strata. So in this way, you can see some close relation among the singularities in Higgs and Coulomb branches. So tomorrow I will explain these correspondence in more algebraic terms by considering the representation theory. So today I stop here. Thank you for attention.
Okay, thanks for the talk. Yeah, I think why don't we start with the question of Aswin?
Thank you, Hiraku, for the talk. So I actually had two questions. One I already posted. So how does varying the mass parameter affect the BFN definition of the Coulomb branch? Real or complex masses, whichever.
Yeah, I think I explained it. So the mass parameter appears. So I consider the Coulomb branch for larger group. So I assume G is contained in a larger group as a normal subgroup. Then the mass parameter is understood as the real algebra element of the real algebra of the quotient group. Then the crucial point is this observation. Maybe, I'm not sure this is known in physics or not. But anyway, so this is not so difficult to state. The Coulomb branch of the original theory is a symplectic reduction of the Coulomb branch of the larger theory. So this is the crucial statement. So once you understand it, then when you take the symplectic reduction, you can perturb the momentum application. And also you can perturb you can introduce the GIT quotient. So the mass parameter appears here. And also, maybe I explained too much detail, but so when you take the quotient, the dual of the real algebra acting on this space appears naturally, but it is isomorphic to because the torus is a dual torus of the flavor symmetry. So this is the element of the real algebra.
Okay. No, so this is the same as saying like real masses, they either resolve the Coulomb branch, and complex masses, they deform. Is this
deform? Yeah, sometimes
is this statement the same as that? That is the sort of thing that we usually say in physics literature, or is this saying more than that? That's what I'm trying to ask.
Yeah, it's the same, but I mean, you must be a little careful. So even if you take generic M, the M Coulomb branch may not be smooth in general.
Yeah, sure. Yeah. It depends on the
yeah, it depends on the gauge theory. Sometimes it is resolution, but sometimes not.
Okay. So I was asking more directly in the BFN definition as the spec of some ring. I was wondering if there was a direct modification of that ring when the masses are deformed. I guess what you're saying is you take what that gives and then do this symplectic reduction to get the mass deformed version. That's what you're saying.
Well, but I described in this way, but the point is how to say. For example, if I change the GIT parameter, then the variety is not a affine variety. So it is not simply the spectrum of the commutative ring. So you must consider the first graded ring, first introduce a graded ring, and you need to consider the project of this graded ring. So you can define KSI projective variety in this way. So I can also explain what is this graded ring. So this is basically you consider the space R tilde corresponding to G tilde, and you have some natural grading on this and take associated grade. Yeah, associated prology of this graded tree. So this is how more directly understand this deformed Coulomb branch.
Okay. Yeah, I have one more question. So the good or ugly condition. So if I understood right, it's the same as saying the balance or something is positive or zero. I think that's what you wrote. So but there are some situations in which the balance condition is sort of like obeyed, but the theory is somehow still bad. If you compute some weights of the C star action, you still get some funny answers. So is that already sort of taken care of in your definition?
Yeah, I didn't explain how the degree is defined. And I mean, if you just imagine the ordinary homology group, the grading is non-negative. So maybe you are puzzled. But in fact, because I take the limit of the equivalent homology of finite dimensional space, in fact. So because when I take the limit, somehow the degree is strangely shifted. So this degree could be both positive and negative. And good or ugly means that this is positively degree, only non-negatively graded, and the degree 0 piece is just correspond to the identity operator. This is what good and ugly theories. And if you have this how to say this Coulomb branch symmetry torus is non-trivial, then you can somehow modify the C star action corresponding to the given by the homological degree. So it could, after perturbation, it could be non-negative. That could happen. The original C star action may have negative weight functions, but if once you modify by TC, it could be non-negative degree. That could be happen. But anyways, our construction covers all the cases.
Okay, thank you.
Pranav also has a question.
Yeah, thank you for a very nice talk. So I have two questions. In this, maybe I'll start with the slide you're on at the moment. So in this definition, you have spec of a graded ring. This graded ring comes from a chain complex by taking homology. So is it ever interesting from your perspective to consider this as a derived scheme and take spec?
Well, yeah, yes, maybe, but I'm not a derived algebraic geometer, so I mean, at least our definition of multiplication is defined on the homology group, and if you consider the multiplication on the chain level, then you must check associativities and commutativities, and then I think that it is possible, and maybe there's some paper, I forget who was the author, but you can consider derived scheme in that way. But I'm personally not familiar with this kind of definition, and I don't know how much in detail it is really defined vigorously.
Thanks. So, and the other question I had was, so you started with this representation, which is this cotangent dual. How much of this theory actually depends on starting with something that arises as a cotangent representation? I mean, is there?
So this is a big good question, and we considered this question, and so we start with M and assume you can write in this way in two ways. So it could be M equal N plus N and N prime plus N prime star. This could happen. For example, if you start with quiver and you consider quiver gauge, and if you change the orientation of quiver, so you get this kind of phenomena. Then we show that the definition Coulomb branch definition of the Coulomb branch is different for n and n prime, but the result is isomorphic. We get isomorphic Coulomb branch. And so before I wrote the paper with Blegon and Finkelgrab, I proposed some approach to define a Coulomb branch for more general M, which is not necessary of this form. But there is some technical issue to justify this approach. And so far, I don't know how to overcome this difficulty in general. But I mean, of course, I know that, for example, if you look at Hanani's paper, he considered more general symplectic representations. And for example, nilpotent of the classical groups. So they are usually not of cotangent type. So I'm really interested in generalizing this definition, but because of technical issue, I cannot give a definition. So this is the current status.
Are there any other questions? If not, let's thank Hiraku again.
Thank you for mentioning.